Hello, everybody, and welcome to this 12th edition of NLP Breakfast. I'm Stefan, broadcasting from Video Office. Our guest is Gregory Sonnet today. Hi, Gregory.
Hi, everybody.
How's it going?
I'm great. Great, thanks.
So, always a pleasure to have a discussion with you. Gregory is the Chief Scientist Officer at XBrain, currently working on human comprehension. And before that, you were a teacher researcher in the French university where you got your PhD in computer science. And you went to the US at Panasonic, working 4 years in autonomous driving and machine learning in general.
Yes.
Today, we are going to talk about language modeling. And first question, what's your take on the recent development?
So if we are looking at the three last year, so there is a huge effort for the community of building some unsupervised modeling for languages. So help to ELMo, Bert, etc. But there is a cost of that is just a few companies are able to build this large model because it requires a lot of resources. And if you want to apply or test it on a specialized domain, and you have to train your own data, that can be very expensive. The cost can be high. So there is a couple of models which are, if I can say, affordable. And one is ELMo. And so we try to make some improvement on ELMo.
Cool,
be able to everybody learn pretty more robust.
We present the XLNet paper here, and the cost is like $250,000.
Oh yes.
And also this pre-model that we can use, they are trained on general news, Command Crawl, or Wikipedia.
Absolutely. Yeah.
And how would you say this lower cost language model can be helpful compared to these high-end expensive models?
Yeah, I'm pretty sure in some specialized domain. I'm talking more about, for example, in our case on XBrain, when we have a lot of data from specialized domain like bank, insurance, but can be on medical area. So you can have a lot of cheap data available because there is a lot of available online or from the customer data. So when you are trying to use this kind of a large model based on Command Crawl, Wikipedia, etc., it doesn't fit pretty well. That's better. So fine-tuning the model or learning a model from scratch by the specialized data for this kind of usage.
Yeah, nice. That resonates a lot for us at Feedly because we also have customers, readers that are in niche markets.
Yeah,
and they always want to top. So this is very helpful for us today. We are very excited to hear your presentation.
Thanks.
And so what is that? Masked ELMo?
Masked ELMo, yeah. So pre-trained language model are a key component for NLP, as we mentioned. And over the last year, so we switched over the paradigm on having a fixed representation of word with a classical embedding, word-to-vec, fast text, and other pretty strong approach. And now we are using contextualized, so dynamic, if I can say, representation of the word. So that's cheap in terms of data because you are grabbing some free data wherever you want. That's free, and because it's a language modeling. So in one way, you try to predict one word according to a certain context for the future. In a middle word according to a context. There is a large number of approaches. I cannot write every approach because there is too much. But if we are looking, there is ELMo, Bert, XLNet. Was presented here, Roberta, all the Bert++, I will say, with some nice sometimes trick, which are able to make the model better. But the thing is, as we mentioned, the transformer approach are, give very high for this, very high results, but the cost is very, very expensive. And if we are looking, I don't know, some number you mentioned, I think the cheaper strong model we can build, it will be one for common guys. If we run some Google credit, it's $145,000 for training the model, which is impossible, I will say. So, and the other side is when we are looking not transformer approaches, but recurrent neural approach. Since ELMo, I didn't see, maybe I miss it, but no new approaches based on recurrent neural network. And I was sad because I like recurrent neural networks, so that's I want to check if I can say at the beginning if ELMo was strong enough to be able to be a little bit better, and we start working on that. So if we are looking at the overview of ELMo, so ELMo for embedding from language models, if so we are taking the word which is read, if I can say, imputed the model on the char level, character level, which is encoded with CNN. Then the CNN are passed through two different LSTM. One is only left to right LSTM, the other right is right to left, and at the end they are combined for predicting the next word for, or the previous word, depending on the direction you are looking at. So usually this kind of model is used as a feature-based model. So you plug another top architecture on the top of that. And usually, so you are not using the only the last representation, but you are combining with a scalar mix the three different levels. So word level, the first layer of the LSTM, the output of the second one with a scalar mix, and that's it. And if we are looking at the numbers, so the thing is due, I think, not only maybe due to limitation, but this kind of model is encoding a pretty small sequence length. They are using truncated backpropagation to be able to have some previous context, but that's kind of short, if I will say. On the other hand, if we are looking on the Bert for bidirectional encoder representation from transformers, a lot of people, of course, know pretty well that. So using the base of the transformers, they are using word piece. They are using a full context, not only left, right, right, left, but all the context together. For doing that, they are using masked LM, and also they are using something interesting, the next sentence prediction. And it's used usually in a fine-tuned model, so you don't have some stuff on the top, and you are only fine-tuning this model for your task, usually, and that's, the performance are impressive. So if we are looking also the number, so think is compared to ELMo, which are using a very large vocabulary, especially for the Softmax. Not only, but here the vocabulary is reduced less than 50,000, and there is different architecture on that, and other improvement after that. So what we propose, think is that if we are looking ELMo, so because of mainly RNN are faster for converging than transformers take a while for be able to converge. You have some trick now, if I can say that's fixed, because you have to warm up the model to be able to have a decent convergence of the model, because sometimes it cannot work. As I mentioned, ELMo is using only a left and right context independently. Bert, in terms of computation, is using a large amount of resources, and especially the memory bandwidth, which is just huge because of attention head and the computation inside the model. Also, even if ELMo is, if I can say, smaller in terms of computation, it's still slow for training. And there is a lot of stuff inside to be able to have more faster model. And some of the choice, I will say, but there is some redundant information on the ELMo representation. For example, the word level for the first layer is just duplicate to be able to fit with the dimension of other layers. Does it make sense? I don't know, but it's, that's maybe for the combination, I will say. So motivation we have for the masked ELMo is to be able to have the full context inside the RNN paradigm, and also improving the speed of the model for training, inferencing, but also resolving some training, I will say, issue in terms of architecture, because when you are introducing some new stuff, maybe there is some improvement you can have. So globally, and I will go quickly on each of the pieces. So contribution. Now, some are of course not new, but we are adding the full left and right context for the ELMo by using masked LM. So we change the architecture of the ELMo. So usually before the ELMo were split into different kind of LSTM. So we are making a more bidirectional, if I can say, LSTM, but by keeping the state projection used in ELMo. We are changing the lexicon by using the word piece lexicon and then simply embedding, enabling to reduce the computation cost. I have a couple of numbers of that. Introduce some in the model some layer normalization. That's pretty important because I will mention later, but for be able to have the representation in the same space when we are combining the left and right, I think it making more sense because usually the dimensionality or the data are not pretty well regularized. We also change some LSTM cells projection, LSTM cells kernel for having more faster model. We are doing dynamic masking. I will also talk about and something which is named bidirectional truncated backpropagation. So if we are looking at the overview of the masked ELMo, it's pretty close to ELMo instead of the beginning of just a token embedding. Okay, so the state for the first layers of LSTM and left to right and right and left are combined, and we're adding additional skip connection in between the layers. That's the global architecture. So, and our training, I will give you more information about this, but we try to not have the best model, but to be able to compare the differences according to the same numbers, if I can say, to ELMo. So we are keeping the state of 4,000. The projection is not 512, but 2 times, 384. And we keep the same architecture, 1 embeddings, 2 LSTM, and if I can say that's it. And helps to what we done, we are able to train on much larger sentences. So thing is, we have some, I cannot say issue, but we had in the beginning some, we keep the same architecture as like ELMo, but we introduce a layer normalization at the end of each of the layers. It helps for better convergence of the model, but also when you are using the model with the scalar mix, because the layers, if I can say, are already normalized, I think it can help a little bit more the scalar mix. And I think in ELMo, in some usage, people are using a layer norm after, but before the scalar mix, but not directly inside the model. So we put the layer normalization inside the model for helping mainly the convergence of the model. Okay, everybody know world peace, but we replace the Charles CNN. It's very, very expensive for training. So when they are doing inferencing, so what they are doing, they are pre-calculating usually the representation of the world. But if you have a new world, you have to compute, and that's pretty slow. And if we have number, when we change this, we are able to increase the speed by 300% because you are reducing the memory. So you are able to increase the batch of the training. And so that's a reduction of 800 to 30K in our case. And word are speed, but the most common word are keep as it is. Okay, so we had the mask language modeling pre-trained objective. So we keep exactly the same number like Bert. So 15% of the word are mask, okay, and the other are keep like this. So 80% are replaced with the mask token, 10% by a random word, and 10% by the same word. Else, because you have a bidirectional LSTM, if you don't do that, you are cheating because you are able to see directly the word in the impute. So we did something. We were kind of worried about the masking, because usually when you do a pass with ELMo, so you have sequence length, you are predicting n-1 word. So according to your impute, the same size, you will be able to read the full sequence and predict almost the full sequence. If you are doing a mask LM, for one sequence, you are predicting only 15% of the sequence. So what we create based on the batch accumulation, something we call mask accumulation. So we keep the same sequence, and on the same sequence, we are doing one inference and one backpropagation over the same sequence with different mask. So in that case, you are able to read the full sequence and have much more word to predict. But there is one trick, because we are using a recurrent neural network. You have to keep, because it's recurrent neural network, there is some initial state of the LSTM. You need to use the same initialized state for all the batch mask accumulation. Else, when you are doing the first mask, you will be able to get all the information of the other word you have to predict on the next sequence. So that's pretty important. Else, it's cheating, if I can say. The model will directly be able to predict the word according to the information provided by the previous mask. So what we did in our experiments, we only did some 4 different kind of masks. So that's 4 times 15%. In that case, we are able to predict 60% of the sequence token, in terms of token, and we read 100% of the sequence. Nothing is masked at the end over the 4 batches, and yeah, 60%. It's kind of in, we can talk later, there is some similar dynamic masking in recent Roberta or other kind of usage for this kind of problematic, for example, XLNet. We implement also something which is a name bidirectional truncated backpropagation. So we start about the problem. If we are looking at the ELMo, there is something a little bit weird. So if you are looking, so that's a mini batch. You are doing your, you're able to see my mouse. Okay. When you are looking the mini batch one, so you have the sequence 0, 1, 2, 3. You are truncated backpropagation. You giving the states 3 to 4, 5, 6, 7. But the main problem is on the right to left context. So you having 3, 2, 1, 0. You trunc backpropagated, and you give the state of the word 0 to the word 7, and you do it again. So all the right to left truncated backpropagation are, if I can say, broken. And I think that can be bad, because if you want to learn some long-term dependency, it can be break. If you want to do it in the perfect way, you have to do for a batch you want to predict, if I can say, the left and right context in terms of inference. You get the state, and you predict, you will be able to have the proper state, initialized state for LSTM. But that's, the complexity is it's too much important. It will increase your training time a lot. So we did something, a small trick. So we changed the order of the batch. Half of the batch sequence are in reverse way. So for the first one, it doesn't change at all, but the right to left state are broken. But on the other one, the sequence are reversed. We have 19, 20, 21, 22, then 15, 16, 17, etc. So, and if we are looking the right two-way backpropagation through time, it's not break, meaning 22, 21, 20, 19, it goes on the other one, 18, 17, 16, and 15. In that way, maybe you will be able to have a proper truncated backpropagation for bidirectional LSTM. So we name it truncated bidirectionally at backpropagation because of that. It's not optimal. So one of the half of the states, if I can say, are broken in terms of sequentiality. But we made some tests, and it shows some improvement in perplexity in language modeling, especially when you are predicting on long sequence, which of course making more sense for looking the numbers. For ELMo, we change something, so I will go faster because we will be short on time else. We move all the projection outside the LSTM neuron, so we move the clipping inside the architecture of inside the ELMo outside. All the projections are outside the neuron, so there is only one change: is this clipping here is not done before the tangency hyperbolic before that. So the thing is, so we make some tests with in terms of perplexity in wiki 2 and wiki 103. It reduced just a little bit the perplexity, but we are able to use a CUDNN neuron, which helps for the training for 20% more. So I think this kind of stuff can be also done in ELMo, basically, because it can help the models to be faster, because optimized by CUDNN. That's a small trick, but also when you are doing masked LM, okay, so you have to only predict couple of the world, not all of the world. If you are doing Softmax for all of the world, you are doing some useless computation, because we are using a dynamic graph. We are able to only do the Softmax only on the world. You have to predict any reduce 50%, 85% of the computation of the Softmax. So some of, yeah, if I can say, a lot of small tricks which are able to make the model faster. And the architecture of our ELMo, masked ELMo, it's more complex, because for one word, it can go on the right, left direction, etc., according to the layer. But with all of the tricks, you are able to balance the computation. So we did some tests with different kind of corpus, but we want to keep the same number with ELMo. So we shift to the 1 billion one corpus to a limited or unlimited Wikibook corpus, and we keep approximately the same number. We keep also same thing, almost the same number as ELMo. We only change something, which is the LRDK, which is more aggressive than ELMo here, but almost the number are pretty similar. Yeah, we are able to reproduce easily with our trick the ELMo perplexity with the basic corpus. For wiki 103, we are able to get a perplexity. So be careful, that's not the same perplexity like usual, but about 16. If we are looking OpenAI, but is only doing the left to right perplexity, which is harder, if I can say, to get. They are having that number. And on our corpus, the only number, if we are comparing to Bert, Nvidia, on the Git repo, they say they are able to get 3.15% in terms of perplexity. Token level, we are able to get 5.9. So that we have a much more limited corpus. It takes something like 9 days for training, and one epoch is 8 hours compared to 19 hours for ELMo with the same setup we have. So we make some tests on the glue task. Okay, so in glue task there is, I will not enter in detail, but there is some task you have to predict at the sentence level, and other you are using two sentences for if the sentence are neutral, it's contradiction or entailment, etc. So there is different kind of tasks. That was good, I think, for evaluating the quality of the model. So we keep the same architecture like the giant repo when they are setting the ELMo setup. We didn't have, I cannot say time, but we didn't want to evaluate all the optimization we want to do. We want to change, if I can say, the ELMo put our masked ELMo and see if the model seems to be much better. So we keep almost the same dropout, number of layers. The top layer in terms of classification are exactly the same, number of batch, etc. We did some just one stuff according to our base model. We try to fine-tune the masked ELMo on the glue task training set to be able to reduce, increase maybe the perplexity, reduce the perplexity on that corpus. And when we are looking the number, so on the validation, so that's what we reproduce with the basic ELMo, baseline ELMo, fine-tune, non-fine-tuning. So if you are looking something which is interesting, but a lot of papers talk about this, ELMo are, if you train a task-specific model with ELMo, when you are fine-tuning most of the time, I cannot say most of the time it doesn't work or doesn't work so well. So the non-fine-tuning, not fine-tuned model of ELMo seems to work better for most of the tasks. So we're having some kind of improvement with the masked ELMo. But if you are looking, I didn't mention here, I didn't have the number on my slide, but if you are looking the numbers for the training part, we saw usually we are having the baseline ELMo with the overfilling training. So all the numbers are almost pretty high. In our model, the model is not able to totally fit on the training, and it makes some sense when we are applying on the test sets. So according to the masked, the ELMo base, we are having a nice improvement from an average of 66 to 70, almost 3. And I report this number. There is no WNLE task because most of people are using majority voting, not on the recent approaches like transformers, but to be able to be fair because the number of ELMo, I think, doesn't have this majority voting. So that's a nice improvement. So when we are tuning the model, it works better. So that means because of the architecture, which is bidirectional, fully bidirectional, I think when we are fine-tuning the model for a specific task, the model improves. So that's good and that's cool for that. And if you are looking the numbers, because ELMo is using the 1 billion word corpus, so I make an online push with the ELMo, which is trained on the wiki plus command crawl data. That's a much more bigger corpus than we use for our training. So the numbers of the tests are much higher, almost 70, and our model is still over that. And if we are looking the GPT first version, not the recent one, which is huge and nice, but we are pretty close to the first, if I can say, result of the transformers published online. So that's also cool. I think we still have some improvement to do on this kind of architecture, but I think it can go over the if I can say, the GPT baseline model. Okay, so, and I think that will be, well, we introduce the fully directional information on the ELMo. We call it masked ELMo. It outperforms the ELMo. So we have, I cannot present here because I don't have the, if I can say, the final number, but a lot of improvement in a different kind of tasks. So we test on the squad, we're having some nice improvements. We test on other tasks, we have still some improvements. So the thing is good because this the model is fast to train. So we are comparing the number for less time than ELMo. We are able to do 24 exactly epoch, if I can say, virtual epoch, because we are doing a mask accumulation. So that's the equivalent of 6 epoch, but 6 for time batch accumulation is the equivalent of 24 epoch. The model in terms of score is very close to GPT first version. We are able to learn on the much more long sequence, so learn maybe more longer word dependency. The model is able to fine-tune, which is not the case of ELMo in almost the task, so that's cool. There is some trick I think you can use for the ELMo base to be able to increase the speed also, which is good too. We talk about the bidirectional truncated backpropagation through time. I think it can maybe help. We need to make more studies on that because I think it can be interesting. And yeah, I think that's it. So thank you, and I think we're.
Thank you very much. Congrats for these results.
Thanks.
And it's very nice to have you explaining here. Thank you for choosing NLP Breakfast to present your results for us. That's an honor
Thanks
for us.
for inviting me.
Yes, just one. In terms of bidirectional versus masked, how do you think each contributed to long-range dependencies?
Now, if I read some recent bibliography, a lot of people with this LSTM, basic LSTM, the gradient vanish after maybe 200 word token. So I don't know if it's the thing is when you are looking the transformer approach, you are using multi-head attention. So with the multi-head attention, that's pretty cool on that way because you are able to get the information almost directly. So maybe the very, very long-term dependency are maybe better. But if you are comparing, and that's what we try to do with ELMo, I think we have you have only a limited context according to this model because it's only and by default only 20 words, which is I think not maybe enough. So that's the thing is we wanted first to be able to have much longer sentence to be able to train but with the default architecture there was not possible to train in the reduced time. So we make at the beginning a lot of optimization to be able to do that, but that was not enough. So and we changed the architecture and introduced masked ELMo because of the problem of bidirectionality. And when you are able to get the full context, all the paper mentioned, and you can see also the same thing on the transformers when you are doing left to right context or the full context. Usually, the full context is better. Just get more information for expression, I will say.
You know, I thought I heard you say that the mask token changes from layer by layer. Right?
No. On the not layer by layer, but we do. So when we do the mask accumulation, so what we do, we keep the same sentence, okay, and for the first time on the same batch, we are having a first sample of the mask. We keep the same sentence, we change the mask, so we infer with backprop, and we accumulate, so the same sequence with different masks at the end to having gradients, which are based on the reading of the full sentence, but also by predicting, in our case, 60% of the word of the token. Sorry, not.
In effect, you're enlarging the data set, basically.
Kind of. So if you're looking, I think the first implementation of Bert, what they are doing, so they are generating at the first. I don't know, maybe it changed now, but you are having the couple of times the same corpus for the different epoch, and for the first sentence and the same sentence on the second epoch, the masks are changed. But the thing is, in terms of memory and computation, that's huge. We didn't have the resources to do that. So the only trick, which is free in terms of memory, I think you can do that, and that's cheap. I will say cheap in terms of computation and memory and resources. That's And the thing is, if you want to know if you're having an impact on the training, I don't think so. Just in terms of computation. But that will be, in our case, we want to ensure, because we are doing every time for the same sequence, random picking of the mask. So if you are between epoch 1, sentence 1, and epoch 2, sentence 1, you can maybe have the same mask, and we want to be sure we mask much more token over the full training. That was just for ensure this. That's it.
So, quick question: when you for the glue task, so you have a single sentence task, multi-sentence task like NLE. How did you train the for the multi-sentence task?
Yeah.
Did you?
So actually, and I think this is not optimal, and that's a good question. That's we keep the same architecture using in the giant repo basically. So we having the first sentence, which is encoded with ELMo or masked ELMo. The other one is encoded independently with ELMo or masked ELMo. So we change something. We give the truncated backpropagation information from the sentence 1 to the other one. That's it, but there is no backpropagation over the two sentences. And I think the right way, so we do some preliminary tests, but that's only preliminary tests, and we saw some improvement on the encoding, like they do in Bert, but encoding the full sentence, and you split, so you are able to backpropagate over the two sentences, and you having, I cannot say large improvement or small, because that's only preliminary test, but that's a good question. And in our case, in our model, because there is much longer sequence dependency, that's better to back through the two sentences in the list.
Yeah, thanks.
Other questions?
Yeah.
There have been some work from Nvidia about mixed precision during training.
Yes.
Where you use like normal precision for the last layers and lower precision for internal layers.
Okay.
And
Yeah.
it has been shown that so it can reduce the memory
Okay.
of the GPU. So it can increase still the performance.
Yeah.
So have you tried it or?
So I didn't mention, but when we do our test benchmark, so for ELMo or masked ELMo, we use partially half precision because of our hardware. That's a 1080. You cannot do a full setup in terms of precision. But the numbers I mentioned, that's using Apex optimization, but we have the same precision for all the layers. But okay, that can be interesting. Okay, to have an idea. Yeah, I have to read about this to see if you can help.
What optimizer are you using?
Adam optimizer. Yeah, but compared to ELMo, yeah, it's more aggressive in terms of LR decay. At the beginning, we having a little bit higher, but the model explodes. So after that's the case for ELMo. The same thing if you keep a too large learning rate over the steps, the model it just explodes. And we have the same thing, and we are able to just adapt this learning rate to stay aggressive, but avoid the model to explode.
You looked at LAM by any chance? You were?
No. Yeah, but okay. Yeah, that's a good. Yeah.
But probably you wanted to just adapt the initial ELMo implementation.
Yes.
To compare.
Yes. Yeah, yeah. So very big, if I can say, main idea to be able to have an improvement, but in terms of bidirectionality, full context of compared to ELMo. And yeah.
A different sort of question. So, are you actually trying to use this in production, or how far do you think it would be from?
So the thing is, yeah, that's a very, very good question, because if you are looking the fine-tuned models, so thing is, it's expensive to be able to fine-tune a big model, large model for each of your clients of your area, etc. Cheaper if it's a field area, okay, but for clients. So that's thing is with a feature-based model, that's good because you have a very basic model which are able to provide some contextual word. And in that case, for a specific customer, client, or whatever application, you can have a more simple architecture, and that's the way we are doing the stuff. That's in terms of production scalability, that's that's better.
But once the model would be fine-tuned,
yeah.
How would be the inference? Would it be
no? That's in that case the goal is to be able to, if I can say, fine-tune if you want the model, but more about the global area field and not a dedicated application. Yes. Else you will have the same issue. The thing is, on that I didn't have the information, but the thing is also making always a comparison between transformers and ELMo. So a lot of paper mentioned something interesting, and this is the case. When you have a lot of when you are using Bert, usually the top layer are not really useful. Why? Because they are very close to the objective function, which is masked LM. And I almost sure this is the same case here. So we're having token embedding. We're having the first layer, but the second layer is close to the objective function. And I think the stuff I would like to do quickly by keeping the same number in terms of parameters and limited the computation, just to increase a little bit the model, maybe 1 or 2 layers additionally, to be able to remove the top layer at the end, and you don't use it for your representation. Because I think because of the objective function, the top layer is useful for the context, but not. It can be much. You can have maybe a much better usage. But you can reduce the weight of the model.
No question. Thank you very much, Gregory.
Thanks, sir.
Thanks for coming. So that's all for today. If you want to present to NLP Breakfast, feel free to contact us, and always welcome to join us, like what you did today, in our Philly office or online. Bye-bye, guys.
Thank you. Bye.
Thank you. Bye.